So last lecture we finished the part on local convergence. And there were two things which I want you to recall. The first thing is that some of the methods, the iterative methods, have this property that we call affine invariance, and that this property is really nice and useful. And you should be aware of the fact that some of the algorithms that we will treat in this lecture, or that people will present to you, they will have this property, and some other algorithms will not have this property, and usually this is a desirable property because it makes you invariant against rescaling of your variables and maybe coordinate system transformations and so on. Yeah, so affine invariance is a good thing. So please remember that, and when people present some very cool algorithm, then think a moment, is it scale invariant? And if it's not, you could easily invent an example, namely just the test example that this guy used, or this lady, to show you his or her wonderful algorithm. You just rescale the variables and you apply the same algorithm, and it might fail miserably, right? So even though it's the same problem. So affine invariance protects you against this possibility that someone can make from the best algorithm, the example on which your algorithm performs so well, someone could not just take the same example, rescale it, and then your same algorithm would be very bad. But it's a good exercise for you when you have algorithmic competitors and they don't have affine invariant algorithms, but they have wonderful computation times. Just check if this is the case or not, because people test usually their algorithms with their own test problems. That's unfortunately so, but that's what happens. And so you can actually very easily come up with bad examples when you don't have this property affine invariance. The other part of local convergence that I wanted to share with you was this property that if you want to see if something converges locally and you don't use the exact Jacobian of the root finding problem, that then you will get linear convergence, and this linear convergence rate is basically determined by one derivative. And I updated the script in the section. It wasn't in the old version of the script, but it's now, since a week or so, it should be there. And this property is that if you solve now this problem f of w equals 0 with an iterative method that iterates like this, which is a Newton type method, where you have a matrix which depends on the iterate and which uses the right residual but an approximate inverse, then you remember there was this kappa condition which compares this with a true Jacobian. Yeah? So m should be similar to the true Jacobian of f. That was our property, but now how similar should it be so that we get local convergence to a fixed point? And we assume that if you really want to have the tightest possible condition, you look, of course, a posteriori, after you know what is the best point, you look at this thing, and then you linearize this map in the neighborhood of this point, and that gives you something which actually says that wk plus 1 minus w star is equal to wk minus w star plus something, and this matrix here is actually the unit matrix minus m at w star inverse times j at w star times, oh sorry, this is not necessary here. This is already in the unit matrix, times wk minus w star plus some higher order terms, wk minus w star. And because we are now talking about linear convergence, you see that this whole iteration will contract if all the eigenvalues of this matrix are strictly smaller than 1, and it will diverge if one of the eigenvalues is bigger than 1. And that's a very tight criterion. So if you want to theoretically investigate the local convergence of a Newton type method, and you regard Newton type methods which have this property that the matrix M depends continuously or even continuously differentiable to make things easier on your matrix, on your input parameter W, and this is, for example, the case for Gauss-Newton method, for the Gauss-Newton method, or also for a constant matrix it would be the case. But if whenever you have this property, you just need to evaluate this matrix at the solution, of course, if you know it, but then you can evaluate the spectral radius of this matrix, and it's either smaller than 1 or it's bigger than 1, and depending on this you will get convergence or not. If it's exactly 1, so if there's an eigenvalue on the boundary of the unit circle, then this linearization-based analysis cannot tell you if it's stable or not. But that's a very unlikely case. Yeah? So the boundary is tight. I would say tight, because this is yeah. So usually it's either smaller or bigger, and it's very, very. You have to tune your data infinitely long in order to get exactly on the boundary of the unit circle in practical cases. Okay, so we have this this analysis. So the spectral radius of this matrix is what really gives you a criterion for convergence which is tight. And this spectral radius is actually more or less what we would call kappa in the other theory. So it's actually the linear rate of convergence. I would like you to consult the script for details on this language and, of course, last lecture. But this was just a summary. It was actually the summary of the first part of last lecture. And now we started to say, okay, this is all nice, local convergence is nice, but you will usually not be very close to this solution. So this all assumed that we are very close to the solution. Yeah? But if you're not close to the solution, then we need something else. And that's where globalization enters, and that's what we started already. And for globalization, we want to make sure that we get this decreasing sequence of iterates. And if necessary, we make our step shorter. So the first part that we introduced was globalization by what is called line search. So we're in chapter 9. And in 9.1, so still recapitulation, we are at globalization with line search. And the basic paradigm here is that we are now in the optimization context. We want to minimize a function f of x, and that we want to create a sequence of iterates which are obtained by xk plus 1 being xk minus bk, where b is some Hessian approximation times nabla f of xk. This is the basic iteration, but this thing we very often called also p. And in order to make the thing a bit more flexible, we introduced another parameter that we call t. And we multiply this step with tk. So basically our step is xk plus tk times pk. And tk is to be chosen by line search. tk is a positive number, and you get it by line search. And this is what we will now explain a bit more in detail. But we already gave one example, and this example, or what we want to do with this t, is actually we want to make the step, if necessary, shorter, so that we get really descent. And also we don't want to make it too short, so that we don't just stay where we are and make infinitely small amounts of progress in every iteration, but don't converge to the solution. Okay, so we need to choose this tk carefully. And the strategy that we have already learned last time is actually to make sure that the new iterate satisfies one condition, which we call the Armillo condition. So one thing that we will, in all line search algorithms, actually require is what we call the Armillo condition. But it's sometimes also called sufficient decrease. And I think that's the better name, even on both. You can call it Armillo's sufficient decrease condition. And this condition states that the new point, the function value f at the new point, xk plus tk pk, that this function should be smaller than a kind of Taylor series of our function along the line along which we look. And this Taylor series is now consisting of our derivative in the direction p. That's the directional derivative in the direction p of our function at the origin. We multiply this thing with tk. And then it gives you, actually that would be the first order Taylor series, but because we know that this will be difficult to obtain, we make this a bit smaller, so we introduce a margin with gamma. where gamma is something typically between 0 and 1/2. So it's a number that is smaller than 1, significantly smaller than 1. Very often one would choose even something like this. Yeah? So it need not be a very big number, it can be nearly 0, but it should be something different from 0, so that it really makes sure that when you make a very big step that you also need to make a bit more progress. Yeah? So it's sufficient decrease. It's not just decrease. Without that term it would just be decrease, but with this term it will be a sufficient decrease. And this is one condition which makes sure that your steps cannot be too large. Yeah? Avoids too large steps. That's what this condition does. And it's always this condition that people use actually to avoid too large steps. But then there's the other thing which we need to make sure, namely that we don't do too small steps. And this condition would be satisfied by arbitrarily small values of t. So I mean, because we are below the Taylor series, the intuition of this whole thing, and I want to maybe call this thing here with a new plot that I didn't introduce yet, but I want to give that plot here. So what we have here, we define a function which I call phi of t, which is just f of xk plus t times pk. So it's the objective function evaluated along the line on which we are. And this function is actually what we plotted here. And of course, its value at this origin at t equals 0 is exactly the same value as f. Yeah? This function will go down because we assumed that we have a descent direction, because actually maybe I should say this one thing. So phi prime at 0 is given by this expression f xk transpose pk. Yeah, so that's a beautiful thing. That means, and this was what we wanted to be smaller than 0 because we assumed a descent condition. But that means that this derivative here is going down. This would be the horizontal. And with this gamma, so if gamma is 1, then we would be here. If gamma is 1/2, it would be here. Typically gamma is even smaller, so it will be somewhere here. So then all points which are below that line would be acceptable for the Amir condition, but we immediately see that when we are very close, all points will be acceptable. And that's actually how it was designed, because we wanted to have a condition which is satisfiable for all arbitrarily small points. But this now brings us to the danger that we could choose extremely small steps and then not make progress. That's happening actually with a lot of things in life, let's say. So if you have very safety aware people, for example in offices or in administrations, they will usually try to avoid to make too big steps and too big changes. And so the big danger of this is that there is sufficient progress to actually adapt to the changing environment, and that's what happens also in university administrations. Look at web interfaces of our university or whatever. So if you don't want to get trapped by this fact that you don't do incremental changes which prevent you from actually keeping pace with the changes in the world, so to say, then you also need to make sufficiently big steps. And in order to make sufficiently big steps, there are many different philosophies. And one possibility, I will present actually another one. One possibility to avoid too small steps is backtracking. And backtracking is also actually resolving directly an algorithmic question, namely how to find a good point that you need that satisfies the Amir condition. And so the idea of backtracking is actually to try a big step first. Yeah, let's say we give some number that we could call T max. And if that satisfies the Amir condition, then you accept it. If it doesn't, and here it doesn't satisfy it, then you divide it or you multiply it actually with a factor beta that is smaller than 1. And then, for example, beta 1/2 would be here. And then this one satisfies already our condition and we would be fine. So this would be beta times T. But if it would not satisfy it, we would still continue and we would divide it again, and then we would have beta squared times T. This was T max. And we backtrack until the first time we satisfy the condition. So I want to write down this algorithm, and I make sure that we have it, because this is the algorithm that we will prove convergence today and that we will also implement in the exercise sheet next week. And so it's an important algorithm and a very practical one. So it's algo 1. It's called backtracking with Amir. And if you think of what are the inputs of this algorithm, it's actually trying to get to give you a step length, but the inputs are actually your current iterate x, your direction pk, which should be a descent direction, then the gradient of fx transpose pk. So this thing you also need in this algorithm. So if you have it already, you should pass it to it and not compute it again. Then you have a constant gamma, that is the one that we have here in the Amir condition, and then there's this contraction factor beta that actually we need to construct, and then I also introduce, and I will adapt the coarse nodes to it at Tmax. I should say that Tmax very often is chosen as 1. But there are some circumstances where 1 is not the best choice and you choose a bigger one. But in all methods that try to be Newton-like, 1 is really a good choice, because when you have the right Newton metrics, you expect that the full steps are the ones that are really helping you a lot, right? So you want full steps at the end of your algorithm. And so by making Tmax equal 1, you will first try the full step and then only make it shorter if necessary. So that's why usually Tmax is chosen as 1. Okay, so the output will be Tk, the best step length. Yeah. And how do you proceed? You just say your value of t is initialized with Tmax, so you give Tmax. Then you actually reduce, and this is now, I think I continue here. So you do a while loop, actually a while loop where most of the work is actually in the condition, but anyway, while this Amir condition is not satisfied, so we actually check if xk plus t times pk is still bigger than f of xk plus gamma times t times nabla f of xk transpose pk. So that was the Amir condition, but it's the inverse. While the Amir condition is not satisfied, you just reduce t. So you reduce it with a factor of b. Maybe I should beta. Beta is actually element in 0 and 1, so it should be smaller than 1. And that's it. And the output is, of course, then tk. You just take the last value of your loop t and you give it out. So it's an extremely simple algorithm. You just check actually if this condition is satisfied. If it's not satisfied, you reduce t. That's what I explained in words before. And that is the backtracking algorithm. And the output is something tk, and this tk is actually that satisfies Amir. That's satisfying Amir. That's for sure. That's how it was designed, but it also has another property. It's also not too short. That means, namely, either it was tk is equal to tmax, or if you take tk and you look at the step before, that is actually tk divided by beta. That was a longer step that you tried before. This step would then not satisfy the Amir. Does not satisfy Amir. Huh? So that's an important property, and we will use that property actually in the proof of not making too small steps. You see what I mean? So what we look, for example, here in this context, let's make one example to be sure. So this would be our Amir condition. This is maybe our nonlinear function. This was, let's say, our first trial, that is T max. Then our beta, so this is all a bit round, but then we reduce this, let's say, by a factor of, maybe we subtract, actually we take always 90%, then this would be beta times T max. It's not satisfying it, then we reduce it again, and we have beta squared T max. We reduce it again, and then we are here. This is beta to the power of 3 of T max, which is equal to Tk, because it satisfies the condition, so we take it. If we take that condition, we also know that this point here, which is actually, it's actually Tk divided by beta. It's just a different way to write what this T is. So this and this is the same. And what we know is this point satisfies the Amio condition. This point does not satisfy the Amio condition. And these two things are needed in order to make sure that the step is really not too small. Yeah? Please note that if you would have, for example, this point here, after backtracking more, you just are a bit too safety aware and you backtrack more, even though you already have your condition. Then you would backtrack more and more, and then you take this value, and then it would not be the case anymore, and then we cannot prove global convergence of our algorithm anymore. So this is a crucial condition, that we stop the backtracking after we have satisfied it. So, of course, if we directly accept the maximum step, then we are done, and this one will, there's nothing, this property doesn't hold, right? But we have then taken the maximum step, and that's not a too small step anyway. So these are the things that we will need. Okay, I think until now I've basically recalled what we did. I decided that I extend this exposition of line search conditions a little bit by introducing a small section into this whole thing, which at the moment, maybe I should call it 9.2 already. I will renumber the sections in the script, and this is devoted to another way to ensure global convergence, and that is called the Wolfe conditions. So just that you have seen already one other example, because there are other examples for globalization by line search. And what the Wolfe conditions do is actually they are not as algorithmic as this one. They first, for A, to make sure that the steps are not too large, they also require the Amio condition, but they basically give the constant gamma, we give it the name gamma 1 because we will need another constant here, but it's the same condition. So this condition says that f of x k plus t k pk should be smaller than f of xk plus tk times gamma times nabla f of xk transpose pk. Until now, nothing has changed. Yeah, that's the same as Amio. But in order to make sure that your steps are not too small, there is another condition which tries actually to avoid that you take a gradient that at the point which you select, actually you require that the gradient is already a bit bigger and significantly bigger than the gradient at your origin. Yeah, so, and here I need to memorize. So what you want is actually that your gradient at the iterate which you want to take, so that is the gradient at the, this is actually the derivative that you get at such points. So that's phi as a derivative at this point. And this phi should be bigger than your gradient at xk transpose pk, so at your original derivative, but it should be bigger by a margin, and I think we introduced the factor gamma 2 here, and gamma 2 should be smaller than gamma 1. And now I think I'm a bit lost. I'm really embarrassed because I didn't write down these things on paper before. So I need to check these things a bit by presenting them to you. But let me first state it with gamma with 0. I mean, we want that the gamma 1, I think, is smaller than this, and the gamma 2 should be smaller than the gamma 1. I think these are the conditions that we want, and I will try to motivate this, and I hope that I didn't make an error now. Yeah? So basically, what I should say is if the gamma 2 would be 0, then you would just require this thing to be already positive. Yeah? The point is that this is a negative number and this is a negative number, so at the moment we are actually just requiring, if you think of what is the gamma, this was gamma 1, right? And now I said that gamma 2, I think I'm wrong. So if I'm, wait a moment, for gamma 1 I would be here, for gamma, I think I need to be more on that side. So I think I need to reverse that order. Let's try that. Gamma 2, gamma 1. Thank you. So I have a ghost corrector in the back, fortunately, that is less embarrassing. And so what we will actually have, if we look at this plot, we will have the Amir condition, which is this line. And we have another even lower condition on which is actually defining only a slope. And what we want now is that maybe I plot a new plot here. That's maybe making more sense. So this is the second Wolfe condition, so to say. And Amir we could also call first Wolfe condition. That's some other name you could give to it. Second Wolfe condition. And you require these two things, and you don't care how you got to a value that satisfies this, but I want to motivate why this makes sense and why we will always be able to find such a value. So this is again t. I will again plot the phi. I will start here. Maybe my function looks a bit funny now. Let's say this thing. Yeah. I have this gradient, and I have the constant, so the 0 line here. And I have my gamma 1, which is actually this thing. So there's the gamma 1 line, from Amir. And now I have another line which is in between, which is, so to say, defined by gamma 2. And if I would use gamma 2, it would be actually, if it would be 1, then it would be here. If it would be 0, it would be here. But I take something in between, and what I now require is that the gradient should be bigger than this line. So this line is not actually a line where the function should be bigger or lower, but it's a line that should be, I can take it as a tangent to my function. So here actually it is tangent. It's also tangent here. If I remove this whole, maybe I take it in yellow, that's or in green even. So this green line, so this green line could be here. It could also be parallel moved here. And I'm happy whenever my gradient is bigger than this. So here it will not be satisfied. Yeah, but from here on it will be satisfied. So the Amir condition is, and now green is not such a bad color. So here's where the second Wolfe condition is satisfied. It's bigger, bigger, bigger. This is even going down upwards, so that's fine. But here actually the Amir condition isn't satisfied anymore. So here I would actually not have an allowed point anymore. So from here to here everything will be allowed. Yeah, so these would be possible Wolfe points. And then I can continue, and I see actually from this point on the first Wolfe condition or the Amir condition is satisfied again. And but this one isn't yet, because I'm still not having the right gradient, so this is not right. But from here, from this moment on where the gradient is again positive, I will have a nice point, and here the Amir condition is not satisfied anymore. So I get this second part of feasible points here. And what you see is already what you would also like, namely that the local minima are in particular a part of it, so you could actually have an exact minimization and you would be fine, and the local minimum will satisfy your condition. Huh? Because your gradient, if this is a negative number, 0, this would be actually, the gradient is 0. If you have really this gradient 0, then it will always satisfy the second Wolfe condition. And okay, sorry, not every local minimum, because you could have a function which goes up here, right? It could be, that would be not an allowed point for the Armillo condition. But all the Armillo points which are local minima, they actually would be allowed, so that's nice. And yeah, on the other hand, we exclude two small values with a different condition. One interesting thing about this is that the Wolfe condition, the second Wolfe condition, it makes sure that one property holds which we will need in BFGS. Yeah? I want to mention that already here. So second Wolfe condition it ensures one thing which is funny, namely that nabla f at xk plus 1 times pk, this whole thing, if it's bigger than this times gamma, then it will also be bigger than if you take gamma 2 being 1. So it will for sure be positive anyway. Huh? So it will be actually, because these are all negative numbers, it will be bigger than nabla f at xk transpose times pk. That means that when we have this gradient and we compare it with the gradient of our next point, let's say, for example, this one here, maybe take that one, then there will be positive curvature due to our two gradients. Huh? And this implies, we will show later, that BFGS remains positive definite. Yeah? So that it preserves positive definiteness of the Hessian. Yeah, you remember this formula that we gave already, but this was actually using the gradient at the old point and the gradient at the new point and the step, which was basically pk, and got from this some curvature into your Hessian, and this curvature is always positive if the second Wolfe condition is satisfied. So that's why one of the reasons why these Wolfe conditions are popular and useful. But here I present them only for completeness so that you know what they are. There is a strong version of these Wolfe conditions, strong Wolfe conditions. And it will just be A is the same. It's always the same, as I said. It's always the Armillo condition, basically. But then B is just making gradients of these two things. Okay, but now it gets the other way around, because these were negative numbers. I think we need to get it like this. So you say fk plus tk pk transpose pk. So you take the norm of this, but then you actually want that it's smaller than gamma 2 times the norm of nabla f at xk transpose pk. And that would be a strong version. And what does it do? Actually, it will actually make sure that you are not only so it will allow these points from here to there, but then it will exclude whenever the gradient gets too large again, when it goes up, then it will also stop. So it will exclude a few more points. So it's more restrictive. That's why they're called the strong Wolfe conditions. And they are a bit more difficult to satisfy. But, of course, these are actually basically two inequalities, because this is a fixed number. This is an inequality on the... Yeah, maybe I could replace it by this inequality plus the negative version of that. And this negative version actually restricts the points on this side, so the gradient cannot become too big. And it will make sure that if you make the gamma 2 small enough, if you make the gamma 2 very small here, yeah, then it would actually make sure that you are very close to minimum of your line, along your line search. Yeah? So that is stronger. And it's so to say closer exact line search minimum. So exact line search meaning the exact line search would actually like to have a local minimum which satisfies the Amio condition. Okay, so these are conditions I wanted to mention, but I will not build much theory on them. You can look that up. Also, these things can be implemented if you want, but I wanted you to know about that. And maybe I should also make as a remark that there exists another set of conditions that's called the Goldstein conditions, which are sometimes used. And again, the Goldstein conditions, sorry, I will just mention that briefly and then I come to the questions. They have still for A, the Amio condition, and then for B, they have something else which is similar to an Amio condition, but I will not explain it because I don't want to confuse you. But they all these sets of conditions, they always have the Amio condition and then something else to make sure that your steps are not too small. And what the backtracking does, it just makes sure that you take the first step that satisfies your Amio condition. And these other conditions, they don't care how you found the point, but at the end, when you found a point, it should satisfy two kinds of condition. The first of which is the Amio condition, the second of which is something, in this case, about the derivatives, and for the Goldstein conditions, it's something should be actually above such a line. So it's actually making sure that you're, so to say, between two rays. But this is a detail. The Wolfe conditions are very popular. Amio backtracking is very popular. And so I think we should restrict ourselves to these two things. But now comes the question.
What does BFGS mean?
What is BFGS? BFGS was something we presented a bit earlier. It was an update formula which took two gradients at two different iterates in order to approximate a Hessian matrix. I will come back to that at the point, but I already introduced the formula actually. Other questions? Okay. What I suggest is that we conclude with possibly more questions or an outlook of what we do in the next hour. And maybe I should directly give you the outlook. So what I want to do now is, after the break, I want to prove that an algorithm that just satisfies the Amio condition and the backtracking, so basically an algorithm that is built on this type of line search that we outlined here, that this has a global convergence property. That means when you started at any point in your optimization landscape, so you just started somewhere, you have some limits on how you could choose these Hessian matrices. Actually, we will assume that the Hessian matrices have a lower bound and an upper bound in the eigenvalues. That's all, but these bounds could be extremely far away from each other. So we just have some bounds on these eigenvalues. And with this proposition, with these assumptions, we will be able to show that the algorithm will go down to, and it doesn't get stuck at the middle of a valley or on the way to the valley, but it will only stop in a point where the gradient is really zero. Or actually, what we will do, and in our proof, we will actually give a tolerance, which can be arbitrarily small. And what we want to prove is that after finitely many iterations, this algorithm needs to arrive at a point which satisfies this tolerance, so that where the gradient in all directions, of course, is zero, or the function that you want to minimize was unbounded below. That means that you can go down infinitely long, right? So that can also happen if you want to minimize the function x with respect to x. You would just go to negative values of x infinitely long, and at the end you will never arrive. But this is, of course, pathological. But once you assume that your function has a lower bound, and your Hessian matrices are bounded below and above your approximations, then we can show that we will converge to a stationary point at least, and we don't stay stuck somewhere. And that's what we will prove, and we will prove it only for these conditions as a kind of example, and similar proofs can also be done for other conditions. But first let's have a break and meet back at 3:10. Conditions clearer based on discussions that came during the break. The first thing is I just want to make sure that the picture that I drew doesn't invite you to wrong conclusions. The point that I want to make is that the function itself, this phi, phi of t, if your t goes possibly infinitely big, then this phi will actually possibly even be higher than your original point of view. So we have a descent direction that only means that the slope goes down, but it doesn't mean that the function itself will always be lower. Of course, it could be that if you go in this valley, think again in the dark in the Swiss mountains, you have this one line, but at the end it could be just that you are going up to Mont Blanc, right? So it's unfortunately it could be really, really high on the other side. Actually, it's even more interesting, and I want to make some other, this is not based on a discussion, but something that I think I want to still add. The question is, why do these Wolfe conditions make sense? And one important question that you should ask is, do points exist that satisfy both conditions all of the time? And if they, in this graphic they existed, right? But do they really exist, and can we prove that they exist? And in order to show that they exist, the first assumption that you would make is again that your function is not unbounded, so there is a lower bound. And the interesting thing is, if your function phi of t has a lower bound, then at some point it will not go down anymore, yeah, for very large t possibly, while this slope will go down. So for sure there will be one point where the Amir condition is exactly satisfied. So there will be one point where this where they connect. Yeah? So where the Amir condition is exactly satisfied. And we have already discussed before that the Amir condition for short enough steps will always be easy to satisfy, because your function is approximately described by the first order Taylor series, and you have a margin because you move it up, right? So up to here even. So there's a lot of room here where your Amir condition, the first Wolfe condition is satisfied. But now to make sure that the second one is always able to be satisfied, the argument, which we can make more elaborate if we would want to, but it's the intuition I can give already now, is that you actually take the initial point, you take the point where the Amir condition actually is exactly satisfied by the argument that I made before, so that point exists. And then you assume actually that your function f is continuously differentiable. That means that there exists a derivative, also a directional derivative, and it's continuous. And by the mean value theorem, you know that somewhere in between, on this function, there must be a point where the slope is equal to the slope of this Amir thing, based on the gamma 1. That is actually this point here in this graph. So there would be one point where the slope is exactly equal to the slope of the Amir condition. And that point exists by basic analysis, calculus, right? And this point already, because the gamma 1 is smaller than the gamma 2, because these are negative numbers, so this point also, as this graphic suggests, it will satisfy already the second Wolfe condition, because it's even flatter, so to say, than this slope. So we have already found one point, which is, so this is like the Amir point. There must be, by the mean value theorem, there must be a point below that satisfies the Amir condition and which has the same slope. And this point, which you don't need to find, but it's good to know that it exists, this point will satisfy both conditions. And so it will always be possible to find a point that satisfies these two conditions. And how to find in the Wolfe conditions, there are elaborate line search algorithms that I don't want to discuss in detail, but they are roughly speaking trying first to find a very large, possibly large interval where you're sure that, so to say, there is a Wolfe point, one point satisfying these two things. And typically it starts by finding some point which does not satisfy the Amir condition, and for example 0. So in this interval you know there must be such a Wolfe point, and then you make your interval smaller and smaller by evaluating points in the middle. And how to evaluate these points in the middle is elaborate and sometimes based on quadratic interpolation, sometimes even cubic interpolations of the points that you have already. And I want not to go into detail. Backtracking, the line search that we implement, is really the most primitive but also already quite effective line search. But of course it will not find something like the minimizer along the line. usually. It will find some point which satisfies some conditions with which we can prove convergence, but it will not find the best point along the line, while much more elaborate schemes would be able to locate a point which is very closely related to the minimum on this line. But I should also warn you that finding the minimum on the line is not exactly what gives you a better life, because you're finding it only on this line. I mean, it was just meaning you're in the Swiss mountains. Okay, that's a two-dimensional landscape. That's relatively easy. But if you minimize and then you have minimized very exactly the center of your line, then you're still not at the bottom, right? So you're just at one valley in the minimum point, but it might still be a very long way in the other direction to the real location where you find your house. Yeah? And that's only a two-dimensional example, but a real optimization problem typically lives in higher dimensions. And if you have a 1,000-dimensional space and you optimize a lot by taking a very elaborate line search and making a lot of work, then you have found the minimum on this one line, then you're very happy and you say, yeah, wow, now I can do my next iteration. And your next iteration will be something which goes into the 999 other directions and actually will destroy the optimality of this direction even. So I mean, this is only valid on this specific line, and once you go into some other place, everything is lost. So it's not optimal really in any sense, because it's only optimal on the line. It's not optimal in the large landscape. Okay. Okay, I will remove that so that we don't get confused from that, because, as promised, we will now prove only the convergence for the Amio backtracking, which is a line search which is good enough. In particular for Newton type methods which try to approximate the true Hessian quite exactly, it's quite an effective scheme, and it's very often used. So let's just prove global convergence of line search and we do it only with Amio backtracking. This is a shorthand. When I say Amio backtracking, it is exactly the algorithm that we described, where you backtrack as long as necessary in order to satisfy the Amio condition. And let me just state the algorithm in general. Newton type line search algorithm, what does it do? You will have some inputs, and so let us specify what will be the inputs. First of all, you need an initial value. Yeah? Then there is some number which usually it's not good practice to give several letters to a variable, but here we do because it's customary. So tol is a number, it's a scalar number that should give you the optimality tolerance. So basically what you require is that the gradient is smaller than this tolerance. Yeah, if you would write that in LaTeX, you should use Roman letters. I just say it to you. Yeah? So tolerance is something bigger than 0. There's this contraction factor beta, which is between 0 and 1, as I said before. And there is the gamma, which is between 0 and 1/2, typically. So that was the Amio parameters, right? That's the backtracking parameter, that's the Amio parameter. And the output of this whole algorithm will be a value that we call x star, but of course this is not mathematically speaking an optimizer, it's just what this algorithm thinks is the optimal point. Huh? I call it x star still. And what this algorithm does, it first iterates, it introduces an iteration index, I call it k, so at the beginning k will be 0. And then you do a loop, and this loop will be actually as long as your tolerance is not satisfied. So what you do is actually while your gradient at the current iteration in this norm is bigger than the tolerance, So as long as you did not find a stationary point, you do something. And what do? You first need to get something like obtain a bk. And we will use a bk which is bigger than 0. So bigger in the metric sense, that means all eigenvalues positive definite. Then the second thing is, this could be, for example, by a Gauss-Newton approximation, by some modification of an exact Hessian, by a BFGS update or so. Yeah? So you first have to evaluate actually the gradient in order to see that your tolerance is satisfied. Then you get a Hessian approximation. Might already use this gradient information, by the way. But then afterwards you get your step, pk, and you compute your step as just bk to the -1 times nabla f of xk. So you actually compute your step. This is only the step direction, basically, but now you still need to do a line search. So now you get tk from the algorithm before, from Amio backtracking. So you put all these things into the Amio backtracking. Actually, if you think of it, in Amio backtracking, we also had the Tmax as a parameter. So this is something we also need to add. So the maximum step length. Then you get this step, and then you do your parameter, and then what you do is actually xk plus 1 is equal to xk plus tk times pk, so that's exactly performing the step. So now we have the new iterate, and you will also, so this is actually, I do it like this, so, and now you update also your index k will be given by the previous k plus 1. Okay, so just to be consistent with the notation, I introduced an index for the x, while I did not, I think that's fine, so it makes a bit, you could of course use always the same variable and the same memory for the x's and just override them. But then you end your while loop, and if you jump out of this loop, then actually this that should be satisfied, and if you are out, then you return by setting x star. You just take the most current value, namely this xk, and of course it will satisfy nabla f of xk smaller than the tolerance, right? So that's what you actually output by definition. Do you agree that this makes sense? So that's summarizing everything we did until now. We said, first of all, we should have a positive definite Hessian matrix that will ensure that we get a descent direction. If we have a descent direction, then Amio backtracking will really make sense. We do that, we perform the step, and then we just iterate until this is met. And now the question is if that algorithm will actually converge or not. And the bad thing that could happen is, of course, first of all, that it just oscillates between 2 points, always making a bit of progress, but converging to something which will never have the gradient 0, or below the tolerance. Or it could also be that this algorithm gets stuck. And these two things cannot happen if we make some assumptions. And most of these assumptions we made already due to this backtracking and the Amio condition. And 2 more assumptions we need to make. And I want to state that all cleanly and then prove it in a theorem, which says that actually this algorithm will stop. So this theorem is actually 9.1. So we assume some things. And the first thing is that f is element in C1, so it's actually a continuously differentiable function. And it should have one more property, namely with nabla f Lipschitz. So the gradient of f itself should be a Lipschitz function. So it's a bit more than just continuous. It's Lipschitz continuous, the gradient. And we make another example, and they exist, C1, so that this is, in the metric sense, smaller than these bk to the minus 1 and C2, which is bigger, with 0 smaller than C1, which is smaller than C2. And I should say that these constants are somehow just needed for the proof, and typically we will assume that there's a big gap between them. This could be maybe 10 to the minus 3, and this could be 10 to the 15, or maybe not, maybe 10 to the 6 or something. Yeah, so we would have a wide range between the smallest and the largest eigenvalue of b, k to the minus 1. This bounds the eigenvalues of this inverse. I should say that I could equally also impose bounds on the eigenvalues of the matrix itself. It's customary, but here I choose it this way just for convenience. And then what does this theorem say? These are all the assumptions already. Yeah? We just take any arbitrary initial value x0, so that's an important point. So you could start anyway. But then, this algorithm 2 stops with success. That means that you have, so to say, an iterate f where this thing is actually smaller than the tolerance. Yeah, so that would be the thing that we like, or f is unbounded below. I don't specify how many iterations your algorithm does. That's a bit unfortunate. It could still be a lot of iterations, but it will not stop, and it will stop after a finite number of iterations if f is bounded below. So this is a short statement. So basically you can give any tolerance that you want, and your algorithm will, if the function is unbounded below, it will stop after some number of iterations. So it cannot get stuck. So that's the theorem, and I want to prove it. And I will do it by a contradiction. That's usually very powerful. And what I will assume, that it does not stop, but that it's bounded below. Yeah? So I basically assume that this thing f of xk is bigger than tol for all k. Yeah, so for all k, that means infinitely many actually. And f is bounded below. And I will actually show that this cannot happen. If this cannot happen, then it must either stop or f must be unbounded below. Okay? For all, k is actually for infinitely many. For infinitely many k. So k is actually going to infinity, and for all values this will not happen. So because we assume that f is bounded below, we have one thing which is already clear. What we have is from Amir. We can make, of course, we know that every step will satisfy our Amir condition. And what does Amir say? It says that f of xk plus 1 is smaller than f of xk plus, and now I can take here this gamma times tk times nabla f of xk transpose pk. That is what we know from the Amir condition. But I want now to reorder these things. I will actually bring this to the other side and collect this and this on the other side, and I write it like this. So I have, say, basically the descent. This is something that, like the amount of progress that I make in every step, which is, this is smaller than that, right? So this should be a positive number. And this positive number, so this amount of progress should be bigger than another positive number, which I got from this thing moved to the other side. So it's minus gamma times tk times nabla f of xk transpose pk. Now, please recall that this is negative. That's why this whole thing is now a positive number. So I actually know that the progress in every step must be bigger than this thing. But this I can also replace by the use of my of my formula for the pk, so I can actually just write this whole thing as gamma times tk times, and I use the f, the nabla f xk transpose, and here I take now b k to the minus 1 and nabla f of xk. And so I have this thing replacing the pk, and the minus sign is part of the pk. And now I use the fact that my bk's are bigger than C1, so I can actually already bound this whole thing by gamma times tk times now the gradient of this thing, nabla f of xk squared, and the factor that I had here, which was C1, because that was the lower bound on my eigenvalues of the bk, so I use already my lower bound here. And so now I know that this will be bigger than that, and I know already, because f is unbounded below, that this whole thing, this will converge xk minus f of xk plus 1. So even if I get stuck, whatever happens, because the f always reduces, and because the f is lower bounded, these numbers, the progress needs to become 0 at some point. So this will converge to 0. That means that this whole thing converges to 0. So what we know already is that gamma times tk times, maybe I put all constants above, so C1 here, but then I have tk times nabla f of xk squared. That will converge to 0. And because these two things are constants, I can also remove them. And this is the thing that I now know. So if I assume that I never stop, but I assume that my f is bounded below, then I know that this product of t times the gradients will converge to 0. It must converge to 0 because of the Amir condition and because of the lower bound on this matrix bk to the minus 1. So now, of course, the only bad thing that could happen, I mean, if this would be constant, it would be fine, because then I know already it converges to 0, and that's contradicting this. But the tk could still become too small, and this is the remaining thing that we need to use. So please note that until now we have already used the Amir condition. So the Amir condition actually makes sure that our steps can never be too big. But what we still did not exclude is that the steps could become too small, and that could happen. Of course, now the tk's could still become very, very small, and if the tk's converge to 0, then this could still remain non-zero. So what we need to make sure now is that we get a lower bound on the tk's, and this is where we need the other assumptions. And the other assumptions were this Lipschitz continuity of f and the upper bound on the Hessians. So these two things we will now need, together with the backtracking. Okay, so what remains? If tk would be always bigger than something that we like t-min, if we can establish that, and this t-min is bigger than 0, then we are done, right? Then contradiction is complete. And that's what we want to show. I want to show that the step length can never be shorter than something like a minimum under these assumptions. So what I will show is actually the following, and I give you already the result. I will show that t-min indeed exists, and it's even given by something, and this is the minimum of two things. It's the minimum of, I should say actually t max, because that's, I need to change the script a little bit to have this adapted. And on the other hand, it's 1 minus gamma times beta divided by L times C2. Okay, there was nearly everything appeared in the algorithm, but one thing didn't, and that was this L. And this L is, I should say what it is, with L being the Lipschitz constant for nabla f. That means actually that we assume that for two values of the gradient, if we compare them, then the norm of these two things will be smaller then the Lipschitz constant times the difference. So that was this extra assumption that I made in the thing above, but now I give it a constant. So this Lipschitz constant is a finite number. Okay, so what we first have, so when we have first for full steps, yeah, that is one possibility what we could have. We will have Tk is be equal to Tmax. So Tmax was the first trial parameter, right? This whole thing holds. So obviously we have Tk is bigger than this Tmin. So I use this definition already. So that's clear. So they are definitely bigger than either this or this, the minimum of the two, right? So they satisfy it. So we can restrict ourselves to the case that we do not do the full step. That means that we have done at least one backtracking step, or two, or three, or four. And for these, we need to show that actually they are also bigger than this number here. And that's what I want to show, and that's a bit, that's actually the only non-trivial part of this whole proof, I would say. But it's doable, and it's not rocket science either. So let me show what we can establish, and the only thing that we know now is that we did one backtracking step, and that this backtracking step was necessary because the previous step was not satisfying Amio. So what does it mean? What we know is that the previous step, which was xk, and then was tk divided by beta. Tk is what we actually did, and beta divided by beta was the previous line search step. So this thing was bigger than f of xk plus gamma times tk divided by beta, because that was the step that we tried there, nabla f of xk transpose pk. So this is something that we know from backtracking. So that's the crucial step already. So please note that this was the backtracking value of t that we tried. So this condition we can just use, and what I will now do is I will actually subtract the f on both sides, and yeah, it's getting a bit tedious, but I think I will still do it step by step. So I will first just say this whole thing here plus tk, so I will just copy this, but minus f of xk, so I put this just on the other side, and then I say this is bigger than gamma tk divided by beta nabla f of xk transpose pk. So I didn't change anything yet, but what I now want to use is I want to use the mean value theorem here. So I have two function values, and this is actually something that I can also express with a gradient at some intermediate point. So I would actually evaluate this at some point which I call tau pk times pk with tau some point in between. Yeah? So tau is element in the interval between 0 and tk divided by beta. So this is just mean value theorem, and it's actually equal to that. Yeah? So this side. Maybe I should put equal sign here. And so then on the other side I can just leave what I had already. Yeah, I think that's fine. No, it's not fine. I think I need to have the step length itself, so I need to have the tk divided by beta also still here, right? Because that's the outside of that. Yeah, so this is what I need. So it's a step needs to be scaled by this tk divided by beta. And now I have the tk divided by beta on both sides, and I can actually simplify my expression a little bit. So what I will now write down, please keep in mind that the tau is smaller than tk divided by beta, but I have now nabla f of xk plus tau k pk transpose pk, and it should be bigger than gamma, and then I leave away this tk divided by beta, and I have nabla f of xk transpose pk. Okay, so now I have something that looks reasonable and nice, and I will actually now expand that even a bit further, and what I will do is actually I will subtract on both sides something like the same thing. So I will subtract this thing here, not with a gamma but with a 1, and I will also subtract it on this side. Nabla f of xk transpose pk. Yeah, so this is something, I just add these two things on both sides, so the inequality will still be valid, right? And now I can actually rewrite this whole thing here. What I have here is actually, I put it like this. Okay, it's a bit funny to write it like this. I write minus 1 minus gamma, so, and then here I put minus nabla f of xk transpose pk, because this was actually a positive number. Yeah? Because the pk was, I will come back to that in a minute, so I just change. So you agree that this is the same as this, just the gamma with a minus and with a minus sign, and here is a minus 1, which is still a minus 1. And what I have here is actually something which is funny. It's actually the nabla f of xk plus tau. I don't even need the index here, pk, minus nabla f at xk, and I take the transpose times pk. That's what I have on this side now. So here is where my Lipschitz constant enters, and here is where my bound on the Hessian will enter. And what I will use now is that this whole thing here is given by, I will use now the p. So I will replace this with my formula. So actually I will use the fact that this is pk transpose bk pk. So it's the inverse formula of my step length, the same formula I used before. So I replace the minus nabla f with bk times pk. Okay. So I still, and here I will actually use that this whole norm here. If I take the norm of this whole thing, it will be smaller than the Lipschitz constant times tau times the norm of p. So these are things that I can already establish. When I look at this, I also note that this is a positive number, this is a positive number. So we are now able to deal with positive numbers. And what we can conclude, because this thing is bigger than that, and the whole, this Lipschitz constant is bigger than this thing, we can actually establish that I should say that the tau is also smaller than tk divided by beta, so we know that this whole thing is also smaller than tk divided by beta pk, right? So this is still valid, and so the whole conclusion is that I can make L times tk divided by beta times pk in the norm that's smaller than this, and then I have the other thing from here. So this norm, I take the norm of the left side, and then I know that this norm for this whole side should be smaller than this thing. And then I take the norm here, and I have actually 1 minus gamma, which is a positive number anyway. And here I take the norm of pk squared from here and here, and then I use the fact that now my largest eigenvalue of bk is somehow also bounded. But the largest eigenvalue of bk, that is an interesting thing. Oi, oi, oi. I'm a bit, sorry. It's, yeah. So what I want is actually that this, yeah. Okay. Maybe I omit one step. I include one step so that it's getting a bit safer, right? So that we don't get lost in stupid shorthands. So the two things that we have already established is this thing, and then what we know is already that because all these numbers are positive, what we know is actually, maybe let me just omit these things for a moment. What we know is that nabla f xk plus tau pk minus nabla f of xk times transpose pk, that the norm of this whole thing, will be bigger than 1 minus gamma times the norm of pk transpose pk pk. So this is actually an absolute value, so it doesn't matter, but I just want to make sure that we have this. And we know already that this whole thing is smaller than this, so we have already established that L times tk beta pk squared is bigger than this thing. I will repeat that for a moment, 1 minus gamma, and then I have here this pk transpose bk pk, and what I want is that this now is bigger than something. And for this I want to look at the eigenvalues of the bk, but this is only bigger than something if the lowest eigenvalue of the bk is bounded. So this must be actually bigger than the lowest eigenvalue of the bk. And here's something that I use, actually I have made the assumption above that bk to the minus 1 is in the metric sense smaller than C2 times the unit matrix. That was an assumption I made. But fortunately, and that's a bit involved, but I will just state it here, is that this also implies that the bk itself, because it's a positive definite matrix, I should also say, I have the property that this is bigger than 1 over C2 times the unit matrix. So it's a bit involved, but this is something that I use here. So I basically do not only bound the upper eigenvalue of bk to the minus 1, but I basically bound the lowest eigenvalue of bk. And that will actually allow me to use now 1 minus gamma times. Here I have now the norm pk squared, and bk will be replaced by its smallest eigenvalue, which will be divided by C2. And now everything is nice and fine. I can actually, these steps pk will be non-zero because the Hessian is bounded and they come from the gradients. So that whole thing implies that t lambda tk divided by beta is bigger than 1 minus gamma divided by C2. Okay, and now I just reorder terms, and I see that tk is bigger than, I bring, here I have 1 minus gamma, I have the beta now on the top, and I have the L and the C2 here, and that is, if I didn't make a writing error, what I had here, a finite number. So 1 minus gamma is positive, beta is positive, L might be very big, C2 might also be very big, but finite. And because these are finite, then there is a minimum step length, and all the steps tk will be at least as big as this one. So we have shown that the t-min is, that this is in fact true, so every step will be bigger than this due to this fact that we had the backtracking condition satisfied, and our proof is ready. So we have shown that there is no way that this algorithm gets stuck. Either it finishes or the function is unbounded below. Okay. That was the argument that I wanted to share with you. It is only proving convergence for line search with Armeo backtracking. It's one of the possibilities. If you would now assume, for example, the Wolfe conditions, then the second part of the proof would be slightly different, maybe easier, maybe a bit more complicated, but in the spirit of it, it will be very similar. Maybe if someone comes up with a more elegant proof, I will be happy. This was, so to say, self-made and not very, possibly not extremely elegant, but it's at least serving its purpose. And the main line of proof was, first of all, that this term tk times nabla f square would converge to 0. That was clear and easy, I think, and clean. Well, everything is clean, but this was easy. And then the second part was a bit more technical, where we had to make sure that our steps really are bounded below and they cannot. So this backtracking procedure will actually under the assumption that we have this Lipschitz continuity, will not go to arbitrarily small step sizes. If you think of the real conclusions of that nabla F is Lipschitz is something that you cannot check easily if you have a large nonlinear function, but you can assume it. And if you think that your algorithm will only make progress, actually it will actually always stay in a level set of your, so you can actually assume this Lipschitz continuity does need to hold only on the level set of all function values which are below. So let's say if you're in the Swiss mountains again, and you have a valley, and in the middle of the valley there's your optimum, which you want to look, where you want to sleep, right? Where your hotel is, then your Lipschitz continuity, you don't need to satisfy it on all mountains, but only in all points in your valley which are below your level set, because you will never visit other points. You only go back down, right? So that's not too restrictive. So you can assume when you have a continuously differentiable function, actually you need twice continuous differentiability and a bounded set, then actually Lipschitz continuity will be satisfied. So that's not bounded. The other thing that you see is that you need somehow to bound the eigenvalues of your Hessian approximations, and that's something that might be a bit nasty. Yeah? And of course, this is something that you cannot, that you usually do not want to prescribe even on your algorithm, but you can observe that it happens. Yeah? So if your Newton's matrices at some point get eigenvalues which are either getting infinitely big or infinitely small, then you would get a problem. And what you could always do is just modify them and have a safeguard to basically make sure that the eigenvalues are always between some reasonable bounds, and that's what happens in some algorithms. Or you would just say, I don't care, I just let my algorithm run, but I make these assumptions in theory, and so my algorithm is sound if I make these assumptions, and in practice I'm not 100% sure if they are met or not, but I would know in principle how to make them satisfied. If you would keep your matrices, for example, constant, so just take the unit matrix all the time, that's actually what we call the steepest descent method. Of course, this condition would be trivial satisfied, so then the C1 and the C2 would be both just 1. And for the purpose of this proof, it would be nice and elegant. It's definitely not the best algorithm in practice, so it's very dangerous to insist too much on these C1 and C2, and I would suggest to, if you want to implement something, to make them very, very far apart in orders of magnitude. So C1 should be extremely small and C2 should be extremely big in order to make sure that you don't disturb your quadratic convergence from Newton type methods. Okay, but in principle we have established a convergence result, a global convergence result. So now we have done in sketchy versions a local convergence with this omega and kappa, and we have looked at global convergence. And I should say that for both areas, for local convergence and for global convergence, you can study lots of nonlinear optimization papers, which will give you a lot of literature on either local or global convergence. So there are many elaborate schemes, but you got an idea of how proofs in these two areas would work. And yeah, that's it for today. What we will do next time is we will look at at some other ways to globalize, which are called trust region methods, and then on Friday we will hopefully also already arrive at derivative computations. But that's it for today, and I thank you for your attention.